Assalamu alaikum. Bismillahirrahmanirrahim. Today again the introductory lecture about the lecture number 4 relating to the course Statistical Inference 1. And today our topic will be the efficiency. Efficiency is the property of good estimator, as we all know. Till now, we came to know that statistical inference aim is learning the characteristics of the population. The population characteristics are parameters and the sample characteristics are statistic. And estimation represents a way or a process of learning and determine the population parameter based on the model fitted to the data. So estimation is of two types: point estimation and the interval estimation. Point estimation, interval estimation, and hypothesis testing are three main ways of learning about the population parameter from the sample statistic. And also that an estimator is particular example of a statistic which becomes an estimate when the formula is replaced with actual observed sample values. Point estimate is a single value that estimates the parameter, and point estimates are single values calculated from the sample. So the confidence interval means a range of values for the parameter. Interval estimates are intervals within which the parameter is expected to lie with a certain degree of confidence, and hypothesis testing means test for a specific value of the parameter. So, and estimates should have the four qualities, which is unbiasedness we have seen, and sufficient consistency we have seen in the lecture number 3. And for the consistent estimator, we have three very important and well-known ideas or theorems of grammar or inequality and its improvement, the Bhattacharya bonds, and also the concept of minimum variance unbiased estimator we have seen in the last lecture. So in our lecture number 4, the third quality of the good estimator we will discuss and see, and the topics under the efficiency that we discuss will be the definition of the efficiency and the some examples relating to it. And the example we will, as usual, we will pick a discrete distribution and a continuous distribution. Then there is also an important concept relating to the efficiency of the estimator is inequality for the correlation between any two estimators. And we will also discuss the examples relating to it. Then there is a concept of best asymptotically normal estimators. And we will also see some examples, or we will check best asymptotically normal estimators in a discrete distribution and in a normal distribution. If I come to the efficiency, and efficiency normally that we use in our daily life, in daily routine, other than statistic, efficiency means useful output with the ratio of total input. But as we are discussing the estimation procedure or techniques, so characteristics of estimation should be unbiasedness, consistency, and efficiency and sufficiency. So efficiency is the third characteristic of estimation. Efficiency, like consistency, is a large sample property. The efficiency of an estimator is usually stated in relative terms. If T1 and T2 are both unbiased estimator of the same population parameter theta, and the variance of T1 is less than of T2, we say that T1 is relatively more efficient than T2 as an estimator of theta. The ratio E, if we call it E, Variance of T2 by variance of T1 is a measure of the relative efficiency of T1 with respect to T2. That is, if efficiency is greater than 1, T1 is said to be more efficient than T2. And for the formula, we know that variance of X sample is equal to population variance over sample size. And then efficiency of of an estimate in statistic we define as the lowest possible variance of T of theta over actual variance of T of theta. So if we see in a rough sketch of a on the normal curve, we have beta hat and beta p, which have a less variance is more efficient estimator. Properties of a good estimator and efficiency is another property of a good estimator, which refers to the size of the standard error of statistic. So the most efficient estimator will be the one having smaller standard error, and standard error we all know is the standard deviation of the sampling distribution. Moreover, efficiency of unbiased estimator, if the estimator is unbiased and the Kramer-Ron bound is the reciprocal of the Fisher information of the estimator, thus for an unbiased estimator T of some population parameter theta, the efficiency of T of theta is expressed as 1 over I T theta over variance of theta. So we can use either the mean or the median. We know that for a normal population, both the sample mean and the sample median are unbiased estimator of the population mean. We choose between them on the base of their relative efficiency. We select that one which has smaller variance is the efficient estimator. Now it means variance of the sample is equal to population variance over the sample size, and variance of median is equal to pi variance of population over 2n for large samples. Thus, for large samples, the relative efficiency of mean is compared to median. And that is, then we divide both the variances and we get the pi by 2 or 1.57, and that is greater than 1. It means that the sample mean is a more efficient estimator relative to the sample median. And this we will discuss in the class in more detail, and we will prove some results or some theorems relating to this topic also. The efficiency of an estimator can be measured by different ways, and the two most important are estimator efficiency as a measure of its precision, and the estimator efficiency as a determinant of minimum sample size is required. So on the basis of this, the efficiency of an estimator is measured of more than one aspects of its characteristics. Properties of a point estimator are different, and the efficiency means the estimator which has the lower variance is the efficient estimator as compared to the other estimators. So if V1 has a smaller variance than the V2, then V1 will be the efficient estimator. This flowchart or this diagram represents this idea very well, that most efficient or unbiased estimator, that from bias to consistency, and we are approaching to the most efficient or unbiased estimators. So this diagram represents the efficiency more clearly, that for the accuracy, you will see all the coefficients have the same values, and for consistency, as n is increasing, they are approaching to the parameter, and in efficiency, you can see the estimator is the best estimator that have the lower variance. And in biasness, you can see as the sample size is increasing, our sample estimates are approaching to the population parameters, and there is no bias between them. They are unbiased estimator. Actually, we want an estimator that should be satisfying all these properties. It should be unbiased, and if there is some degree of order of biasness, then we call it asymptotically biased, and we try to remove it, or by finding its order with the help of some results. Then we see whether it is, if we see it is unbiased, then we move forward towards the consistency, and we see the estimators, we select the, we find out that the estimator, those have larger sample sizes, are more consistent, and their estimates are approaching more quickly and easily to the population parameters. And similarly, in efficiency, we are also seeing, finding the best estimator, and the best estimator is the that estimator which has a smaller variance. Otherwise, it is inefficient estimator. OLS, over in this slide, it is also given that general least square or 2 SLS are insufficient, efficient, but OLS is more efficient in our example than MAD. So properties of the OLS estimator, we can see the variance of an estimator is if less than the variance of the other estimator, then we call it an efficient estimator, and it should be unbiased also. Typically, if we see the definition of the efficiency, then we can define it that for an unbiased estimator, efficiency indicates how much its precision is lower than the theoretical limit of precision provided by the grammar or inequality. Actually, we all know in statistical inference what we are doing, we have to make the decisions. Decisions about what? About the population parameter. Because sometimes population is unknown, some population is undefined, or maybe some its parameters are missing. So on the basis of sample, we try to find out the parameters. So all time in statistical inference, we are after the parameters. We want to find out the parameters. And parameters can be, we know, find out by the help of sampling and estimation theory. So estimates we should select, and we want to select the best estimates, the good estimates. And the good estimates, for the good estimates, it is compulsory, or it is our assumption that they should be unbiased, they should be consistent, they should be efficient, and they should be sufficient. So for the unbiasedness, we know that our sample mean should be equal to the population parameter. It means there is no difference between the estimated value and the actual values. And if there is some difference, then it is called the bias, and we try to find out the error order of the bias. So in the consistency, we see if the sample, those sample sizes, samples that have large sample sizes are consistent. So we try to find, select those estimates which are unbiased and have large number of samples, have a large sample sizes. Then we, for the estimates, we, if the last two properties are satisfied, then we should see their efficiency. And efficiency means we compare their variances. And if they have low variances, so it means that the system is doing well, because the Small variation in the system indicates the system is showing normality. So the estimators or estimates that have smaller variances are efficient also. So we try to pick the unbiased, consistent and efficient estimators. And in our coming lecture, lecture number 5, we will also see what is sufficiency. So sufficiency is, in short word, the estimate that uses the more information as compared to the other estimate, and it is called sufficient. So we try to select that estimate which is unbiased, which is consistent, which is efficient, and also sufficient. So that will be our required estimate, and we will pick it uh, with the assumption that it will follow the population parameter. So efficiency is also means the precision. It indicates the precision. And in theoretically, we have the Kramer inequality. That is and its improved forms. We have Bhattacharya bound. And similarly, if we see the idea of efficiency, then we have the relative efficiency of our estimate or estimators. So these all are to get the consistent and efficient estimates. As we have the idea about or the concept about the asymptotic biased and estimates and asymptotically consistent estimate, that as similar we have the asymptotically efficiency we have. And it means for a biased estimator, asymptotic efficiency is the limit of its efficiency as the sample size tends to infinity. An estimator with asymptotic efficiency 1.0 is said to be an asymptotically efficient estimator. So, estimated relative efficiency should be equal to R minus 1 into MSBL plus R into C minus 1, MSE mean square error, and RC minus 1 means RC minus 1 into mean square error. Estimate the number of observations in each treatment group needed to obtain the same precision for comparison of treatment group. Means as with randomized block design. Nj without blocking is proportional to Re into R with blocking. So this is the concept behind the estimated relative efficiency. Then efficiency, if we see its another definition, efficiency can be defined as an unbiased estimator is said to be efficient if it has lower variance than all other estimators. For example, if we compare two unbiased estimators, V1 and V2, and then V1 is more efficient than V2 if variance of V1 is less than variance of V2. Kramer bond is a lower bound of the variance of any unbiased estimator. Then an estimator is said to be efficient if it is unbiased. It satisfies Kramer bond also. Efficiency of an estimator we can see with the help of variance, and the variance formula we already know that it is equal to 1 over n into sum of y, or which is equal to 1 over n square into sigma, sum of sigma square, and which is equal to sigma square over n. If we compare the consistency and sufficiency, yet we have not discussed the topic of sufficiency, but it means an estimator is said to be consistent if its probability of being close to the parameter is estimates increases as the sample size increases. And for the sufficiency, an estimator is said to be sufficient if it contains all the information in the data about the parameter it's estimated. So consistency means n is equal to 10 to n is equal to 100. As sample sizes are is increased, we start approaching to our parameters. Most efficient estimator we will see, and we will follow the same procedure, that those estimators which have the smaller variances are more efficient. Then in actual word, efficiency is meant by an estimator is efficient if it has a relatively small variance and standard deviation. An efficient estimator is on average closer to the parameter being estimated, and an insufficient estimator is on average further, means far away from the parameter being estimated. So important and special cases of the consistency or efficiency are given below. It will help you to understand the concept behind the efficiency very well. And we will also see them mathematically by algebraically. We'll see their manipulation in the class, and we'll see some theorems or some results proofs, and also some examples relating to this topic as an exercise. So thank you, class, and this is all for the today's topic relating to the chapter lecture number 4. Thank you and Allah Hafiz.